Let's get started. So first, this is my last lecture. I really enjoyed getting this opportunity to come to Moscow and give this series of lectures at the Higher School of Economics here. I would really like to thank Professor Konakov for inviting me and organizing this series of lectures. So, and of course, thank you to all of you for coming, and thanks to those who came to other lectures but aren't here, thanks to them as well. So today I'll talk about a topic that's quite different, I think, from most of the topics that I've discussed. It's a bit more statistical in nature, but it maybe corresponds a little bit to some of the kind of overall ideas I've talked about. Several of my lectures have been about the fact that we can never, from a finite data set, we really don't know what happens in the tails. And we make various parametric assumptions about the tails, even though they're very likely to be wrong, and yet they do have consequences. And that, to an extent, was what I was discussing, that certain things that are, certain asymptotic results really depend on what happens in the tails. And maybe the sense in which this relates to that kind of discussion is this is an approach to how we can talk about tails in some non-parametric way. It's a very different perspective in a very different situation, but it still tries to talk a little bit about the tails of distributions. So this talk is Turing's formula and its statistical implications, and basically the first part of the talk, not really the first half, the second half's a bit longer, but the first half I want to introduce Turing's formula and discuss some of its properties. I assume probably many of you have heard of Turing's formula, but in general, it's a tool which seems to be used very widely in ecological applications and in linguistic applications, but I haven't seen too much work on it in other statistical contexts. So I want to discuss it a little bit, and then I will talk about estimation of various quantities, of various quantities that we can use, kind of using ideas coming from Turing's formula. And in particular, the kind of quantities I'll be talking about is estimation of Shannon's entropy and certain related diversity indices and related distances. So first, before I get started with the majority of the talk, let me just introduce the main notation that I will be using throughout this talk. So X is a collection of letters. We assume it's a countable set with cardinality K, which may be finite or infinite, and the cardinality may be known ahead of time or it might be unknown. So in linguistic applications, the letters tend to be words. In ecological applications, the letters correspond to different species. For each letter, we assume there's some probability distribution. So P is this probability distribution of little pk's, where pk is the probability of observing letter L sub k. And we assume we have some sample from this distribution of letters. Of size n. One thing to note, of course, about a sample of letters, it's not random variables because the values we observe might be species, they might be words, they're not necessarily numbers. So n is the size of our IID sample from this alphabet, and we can summarize the information in this sample in the following way: let yk be the sample frequency. So that, it says frequency, but what I mean here is the number of times we actually observe the letter. So this is actually sample counts of Lk, and pk hat, that's yk divided by n, is the sample proportion of this letter Lk. So to motivate the discussion, let's consider a very an example from ecology. So in this case, we're observing different birds. So we're looking at, we're somewhere in a particular location. We're looking at what kind of species of birds we observe. And so our letters are just different species of birds. And we don't know the underlying proportion of different birds in the population. We probably don't even know exactly what species are there. There might be some birds we've never seen before that we might observe. So assume we take a sample. Let's say the sample's of size 2,000. So we've observed 2,000 birds. And we observe, okay, 300 of them are of species 1, 200 of species 2, and so forth. And the corresponding proportions, maybe P1 hat is 0.15, P2 hat is 0.10, and so forth. There are estimates of P1, P2, etc. One way to interpret these P hats, of course, is if we ask, well, what's the probability the next bird is of type 1? Well, roughly it should be about 0.15. But now let's think of it. We have observed this sample, and let's say maybe we observed 30 different species. It's very unlikely there's only 30 species in this population, and yet if we go back to this idea of looking at the pKs as our estimates for all the probabilities, then what we're basically saying is that the probability that the next bird is one we have never seen before is 0, even though we know that shouldn't be the case. So what can we say? How can we what can we say about the probability that the next bird that we observe will not be one of the species we have seen thus far? So that's the kind of idea that Turing's formula gets to, and I'll get to the formula in just a little bit. But I want to first go on to maybe a second example to motivate the discussion. So let's say we have 100 marbles and 100 buckets, and we just randomly throw the marbles in the buckets, assume with a uniform distribution. And at the end, when we've thrown all of our marbles, we look at the buckets and see how much we have, how many marbles are in each bucket. And so how many empty buckets do we expect to see? And it's not a difficult calculation. We could see that it's about 37 buckets that we expect to be empty. Now, how many buckets do we expect to see with exactly one marble? It turns out if we do the computation, it's also approximately 37. And this result is basically due to Turing's formula that relates the number of kind of buckets that which we could say we haven't kind of observed, we have no marbles in, with how many have exactly one.
May I ask,
yes.
Do you understand correctly the first example about the birds? So,
yes.
So the sum of these pi's is not equal to 1.
No, the sum of the p. If we go back to the beginning here, the sum of, this is a probability distribution, so the pKs all add up to 1. But now we need to estimate them because we assume we don't know them to begin with. So we see a sample of size 2000, and based on that we get our p hats. And the p hats will also add up to 1.
But you told us that it can be that some birds are from some species that we do not know. Unobserved.
Yes. So that's the problem with this. So this is kind of the standard approach. This is the MLE for the proportions. Is these sample proportions? But kind of the problem with the MLE is that it says that kind of if we just use the MLE as assume it's a good enough approximation to the true distribution, it tells us that there are no other species. So so if we just look at the p hats, we would say, okay, probability next one is one we haven't observed. Well, it has to be 0 because the p hats all add up to 1. And yet, intuitively, we don't believe that there's only 30 species in the population. So there should be some additional probability for those other species. And yet we have, using this approach, we're estimating that probability to be 0, even though we know that's an underestimate.
The popular question is that how many words do you believe Shakespeare used to know? If you know the corpus of his papers, huge literature of this type. So there's different estimation. But maybe, I don't know, was it from Turing directly or from...
It wasn't from Turing directly. He never published about this, but there is a very large literature.
Okay. But they were also talking about Turing.
Yes.
So if you know the corpus of Shakespeare papers, would we say what is the number of words he actually used to know?
Yes, it's a similar question, and I've seen some papers on that question, and I'll later give an application which is not exactly that, but related to that question. But yeah, again, if we use the p hats for that case, we'd say, well, he only knew the words that were in his work, but of course that's not reasonable to make that assumption. So how can we make those kind of estimations? Okay, so here's our two examples. So now, how do we estimate the number of species we haven't observed? And Turing's formula starts, well, we need to make a couple of definitions. Let n1 be the number of species we observed exactly once, right? The sum of the indicator of all the yks, wherever yks are the counts of species k that we saw exactly once in our sample. nr, we can define in a similar way how many species we saw exactly r times. And pi 0 is the probability associated with letters that we did not observe. So it's the sum of the pKs of the species that were not observed. And what we want to estimate is pi 0. One interesting thing about pi 0, which makes estimating it, I think, maybe a little bit different than most things we estimate, is usually what we estimate, would be things like the pKs, probabilities, things that don't depend on the sample. Pi 0 is interesting. It simultaneously depends on things that we haven't observed, things that we don't know, and at the same time also depends on our sample. So we want to estimate something that both depends on the sample and on the unknown distribution. So Turing's formula, it basically just says, okay, T1 is n1 over n, and n1, of course, is the number of species we saw exactly once. So we just take the number of species we saw exactly once divided by the size of the sample. And this is a good, and I'll maybe try to motivate a little bit what I mean by good, but this is a good estimate of this pi 0, the probability of things we haven't observed. In some sense, we could think of this as kind of the tail of the distribution in some sample-dependent way. Right? Usually this will be relatively small probabilities, and this is the thing that we're interested in estimating. And so this was, although this formula is usually credited to Turing, actually he never published anything on this formula. This was originally published by Good. I have the reference a little bit later.
Robinson.
Yes, I'll mention some more literature. Robbins also worked on this problem, as have a number of other people. I'll talk a little bit about the history in a little bit. So sometimes this is called the Good Turing formula because Good was the first one to publish it, but even as he was publishing it, he gave complete credit to Turing for it. Yes?
I have one question. Are there some results giving the performance of this estimate? Because I'm surprised because P0 moves as the number of observations. The more you gather observations, the more P0.
Right. I'll give some results to help motivate how this works and why it works. But of course, yes, this thing, of course, is going to be approaching 0 as the sample size goes to infinity. So it's generally a very different type of object we want to estimate than usual because it's sample dependent.
I mean, maybe it's in the rest of your talk, but are there some results showing, for instance, that for a given epsilon, the probability that the difference is bigger than epsilon is smaller than something?
There are no such results that I'm aware of. There are certain kinds of results that I will discuss, but none as that would be a very nice result. That would really explain Turing's formula. What I can say is Turing's formula has been analyzed in terms of simulations quite a bit and does a good job. And in terms of some other ways of looking at it, I will get to in a couple of slides. But no, it would be very nice to have that kind of answer. And I don't think I'm not sure that something like that would be plausible because of.
Actually, sorry.
Maybe this set is empty, then unobserved species.
If the set of, it's possible that we've observed all of the species, although in that case it's likely that there'll be very few, there'll be very few species we've only seen one of relative to the sample size, and so T1 should also be very small in that case.
In this case, it's also covered by this.
Yes, this, I mean, at least as an estimator, this can be used in any situation. I can't say we'll always give it, give it. I mean, how good it is as an estimator. Well, there's various ways to think about it. Okay, so this is the estimator, and now let's go back to the to our examples and discuss them a little bit. So for the bird example, right, we had a sample size of 2,000, and let's say we had 12 species that we observed only once. So we would estimate that the probability that the next species will be one we haven't observed to be about 0.6% or 0.006 is the probability. A separate question is there a way to incorporate this with our p-hats, right? Because we know that the p-hats add up to 1, right? So in some sense, this additional probability, if we throw that in, things will not add up to 1 with this additional probability. And there's different ways to try to adjust the p-hats in order to make things add up to 1. I'm not going to discuss that in this talk, but there's various smoothing approaches to try to modify the p-hats in order so that we could use Turing's formula to estimate everything we haven't observed and still estimate all the other probabilities and have things add up to 1. So that's...
Could you give some intuition why at least this estimator is unbiased?
Yes, so I will do that. I will give some intuition about it in the 1 or 2 slides. Okay, just to talk about the bucket and marble example, where we had a sample size of 100, so then pi 0 is, by definition, the number of empty buckets divided by 100, which...
The reader says that, explain in my book what is possible to say about this. Okay.
Okay. Oh, so okay. You've worked on this problem.
It's in my book. Everything that was known about 6 years ago, about 7 years ago about this problem.
Oh, okay. Well, that's. I wasn't aware of that. That's definitely a good reference.
You read Russian, yeah?
Yeah, maybe we can continue. So, okay, so getting back to this marbles example, right? So pi 0 is exactly the number of empty buckets divided by 100 in this situation. And that, we believe, can be well approximated by Turing's formula, which is number of species that, or number of buckets that only have 1 marble divided by 100, which is about 37 out of 100, or it should be about 37 out of 100. And we can also see that n0, the number of empty buckets, is also about 37. So we kind of see Turing's formula working in this example, or how it would work in this example. One thing I do want to add is that the sample that we have, 37 empty buckets, 37 buckets with, on average, 37 buckets with about 1 marble does not look like a very uniform sample. And of course, even though it comes from a uniform distribution. Now, of course, in this example, we could figure out why we would wind up, getting some buckets that have a lot. We have 100 equally likely buckets and only 100 marbles. But one thing this Turing's formula can kind of help us to do is to see. Although the sample doesn't look uniform, roughly because we don't have a large enough sample in order to deal with the number of buckets we have in the distribution that we have. And I think one thing Turing's formula helps us to think about is what does it mean to have a large sample? If we have a lot of kind of buckets or a lot of letters that we haven't that we've only observed once, that kind of suggests that we don't really have a very representative sample. So even though here we have a sample of size 100, which if we knew nothing about the problem, we were just trying, if this was maybe the birds situation that happened to also be this kind of a uniform distribution on 100 species, from this sample we think, well, a sample of size 100 is not a very small sample, and yet it might not be very representative. So I think Turing's formula also gives us some idea of whether the sample that we have is kind of has a lot of coverage to it or not.
In my version, I don't remember why, but I doubled this number. Could you comment why you have different formulas? Because what I wrote some 7 years ago, that this number should be doubled. To get number of unseen species, you should take ratio one unseen species divided by one number and double it. But I don't understand why we have different formulas for the same problem.
I'm not sure. Turing's formula that I've seen is in this form, so...
I'm pretty sure that you should double it.
I don't know. I'd be happy to discuss that with you more, but this is how I've seen Turing's formula. Okay, so how can we interpret this, this formula? So recall what we want to estimate is pi 0, which is the sum of all the probabilities of the...
Sorry, I took Poisson distribution with another parameter, but you took which distribution?
Just a general distribution on the alphabet. Okay, so again, so we want to estimate the sum of all the probabilities for letters that we have not observed, and our at least proposed estimator is this Turing formula, which is the number of observations we've seen exactly once divided by the sample size. So how can we interpret this formula? Well, one thing we could note is, again, note the thing we're trying to estimate is random. It both depends on our sample and on things that aren't known. And so we can ask, well, what's the expected value of pi 0? And it's a very simple exercise that this is just the sum over all the letters, pk times 1 minus pk to the power n. So that's expected value of pi 0. Now, what about expected value of Turing's formula? Well, again, it's not difficult to see, right? That's right. On the top, it's basically the probability, right? We can take the expectation, and it's not difficult to see. We get essentially a binomial distribution, and the probability and the expected value of the numerator will be given in this form, just from a binomial distribution. Oh, good. Yeah. Okay, and then we can simplify this a little bit, right? Kind of cancel the n's out, and we wind up with this formula. Now, of course, these are not exactly the same. Here we have n, here we have n minus 1. But still, for large n, this will be approximately similar to each other. So we could think of that, at least in expectation, these two things are close, although it's not exactly unbiased, right? Even it's not unbiased for the mean of pi 0, but in some sense, for large n, they will be quite close. Now, a different way of thinking about it is due to Robbins' 1968. And Robbins thought of it this way. Let's say we get one more observation. If you give me just one more observation, then I could make this unbiased. But what do I mean get one more observation? We get one more observation, and we update Turing's formula. We get T1 plus. We update Turing's formula, and we get a new estimator based on this one more observation. But we don't update pi 0. If we do that, then we get that the expected value of this kind of give me just one more observation estimator is exactly has exactly the same mean as the expected value of pi 0. So this was how Robbins tried to explain how Turing's formula works. So now let me just give you a brief history of Turing's formula. So in 1953, Good published this formula in Biometrica. He tried to motivate it using some empirical base formulation, and that was the first time it appeared. He gave credit for it to Alan Turing. I think this was just a year or so before Turing's death, and I don't think he was working on these kind of problems, but that's kind of the origin of the formula. And then in 1968, Robbins tried to explain how the formula works, and he gave this intuition that if you give me one more observation, then we'll have a kind of an unbiased formula. In 1983, Esti published a paper where he gave a sufficient condition for Turing's formula to be asymptotically normal. Although it's asymptotically normal in a specific sense, he assumed that the distribution, the pKs, are changing. And the k, the number of letters, is growing, and the pKs are changing. And he gave some conditions under which, in this kind of scheme, Turing's formula T1 minus pi 0 under some normalization will converge to a normal distribution. But it turns out that there's no fixed distribution for which this holds. You really need to change the probabilities quite a bit. And then, so this is more recent work by my collaborator on much of the work I'll discuss later. And he, with co-authors, so in 2008, found a sufficient condition for Turing's formula to be asymptotically normal. And later in Zan and Zan 2009, they found a necessary and sufficient condition for Turing's formula to be asymptotically normal.
And what?
Oh, N2, remember, so N1 is the sum of observations that we saw exactly, of species we saw exactly once. N2 is those we saw exactly twice.
Which terms these conditions are formulated?
So they're somewhat complicated. I don't remember them exactly, but they're in these papers. Okay, so that's just a little bit about Turing's formula, which is something I find very interesting, though I have not worked with it, that I wanted to give as background. And now I want to discuss some statistical implications of Turing's formula. If we use kind of ideas as in Turing's formula, we can get some nice estimators for various quantities. And the first quantity I want to discuss is Simpson's biodiversity index, sometimes also called Gini-Simpson. Sometimes people work with a slightly different version, which is sum of pk squared. But I'm going to work with this version here. Of course, that version is just 1 minus this one. So it's not a major difference. So this is a common index used to talk about diversity, probably most commonly used in ecological applications, although it's also used in economic applications and in linguistic applications, talking about the diversity of an author's, the word choices of an author. So one way maybe to think about this, for each probability pk, we kind of weight it by 1 minus pk. So in some sense, we weight smaller probabilities a little bit more than larger probabilities. So we can think of it, we maybe want to weight, if we have a lot of we have a lot of species that are less common, we might want to weight them more because there might be a lot of them and they really contribute a lot to the diversity. So we don't want that to be kind of forgotten. So this is that's kind of one intuition behind this formula. And of course, the most common way to estimate this is just a plug-in estimator. We take pk hat times 1 minus pk hat. It's maybe the most natural, the first thing we think of as to estimate this thing, but this is a biased estimator.
Well, why you want to estimate 1? Better to plug p hat in pk squared, because that is 1. So what's the argument?
And
To
because in
estimate
this
one-
form, it seems better to
Okay.
don't touch.
This looks better statistically if you want to plug.
That might be true for the plugin. So I'll talk about a different approach where this is the form that I want to work with. I mean, ultimately, it's the same thing, right? This is 1 minus that one. So however you plug it in terms of bias and any kind of properties, it's basically going to be the same.
But you estimate 1 by the sum of p.
Sure, yes. So the reason I present it in this way is because I'll talk about a slight generalization of Simpson's index, generalized Simpson's index, which was, as far as I know, introduced in Zhang and Zhao 2010. And here, basically, instead of weighting by 1 minus pk, we weight by 1 minus pk to the power v. And the intuition is that this gives us a somewhat different weighting scheme, and it's although when v is larger than 1, it will be the whole index will be a little bit smaller, but in some sense we weight the smaller probabilities more relative to large ones than we did when v was just 1. So in this kind of thinking about weights, this might be a reasonable way to also talk about diversity. And one interesting fact is it can be shown that the collection of these generalized Simpson's indices uniquely determines the distribution, the P1, P2, and so forth, up to permutation of the P's. And in some sense, it gives us a reparametrization of how we can talk about the distribution. So instead of talking about it in terms of pKs, we can talk about it in terms of generalized Simpson's indices. And perhaps one advantage to thinking of it this way is that every single one of these indices somehow says something about the tail. Whereas if we just estimate the P's by themselves, each one just says something about one species. Whereas here, every one says something about all of the species, including, in some sense, ones we haven't observed yet.
Is it a misprint, so the collection you mean not n but v?
Oh, yes, that's a misprint. Thank you very much. That should be v. Thank you.
It's exactly the reason why you're considering this index with natural v.
Yes, yes. We could consider it with real v. And I don't think I talk about it here, but the methodology I'll later discuss will be useful in that case as well. But I'm just assuming that it's integer values for now. Okay. Yeah, but n I want to save as always referring to the sample size. So so now assume we have a sample of letters or species on our alphabet, and our sample is of size n. Now let's think about the generalized Simpson's index of order n minus 1. So just one less than the sample size. Well, this is exactly, remember, what we saw earlier with Turing's formula. Turing's formula estimates this thing in an unbiased way. So we have an unbiased estimator for this thing. T1, just n1 over n. Turing's formula can estimate this perfectly. Now, of course, this is just for n minus 1, or just one less than the sample size. But at least for that case, we see we get a nice unbiased estimator. And actually, we could use this idea for other generalized Simpson's indices as well. In fact, we can kind of use Turing's formula, and I'll explain what I mean by that in a couple, maybe next slide or in the next 2 slides. But we can use ideas based on Turing's formula to get unbiased estimators of zeta v, these generalized Simpson's indices, for any v from 1 to n minus 1. However, the approach that I'm discussing will break down and will not work for v greater than or equal to n. And in some sense, I haven't proved this, but I conjecture that there probably is no unbiased estimator for when v is greater than or equal to n. I have some reasons for thinking that, but I haven't proved it yet. So I'm not sure. And one thing to note, if we could estimate it at not at n minus 1, but at n, then we would actually be at least estimating the expectation of pi 0, and not in this kind of approximate way or give me one more observation kind of way. So if we could do that, but at least I don't know how to, and as I said, at least I conjecture that probably it's not there's no unbiased estimator. Okay, so how do we do this? Okay. So I'll derive an unbiased estimator. So let v be between 1 and n minus 1 integer. And we want to again estimate this generalized Simpson's index. So now consider we have this random sample x1 through xn of size n. X's, of course, they're not necessarily random variables. They could be, right, because random variable we think of as a number. But here this could be species, birds, so forth that we've observed, words, letters in general. Okay, now let's take a sub-collection. Just randomly choose, randomly sample a size v a size.
Why v plus 1?
Yes, that's a typo. This should be up to v plus 1. Yeah, this is x1 to v plus 1. Apologize for that. That's a typo. So get a sample of size v plus 1. And now let n1 circle be the number of observations in this sample that we see exactly once. By the same argument as before, basically by Turing's formula, for the subsample, the number of observations that we would get by the same exact argument as before that the expected value of kind of the Turing's formula for this subsample will give us exactly zeta v. So now we have an unbiased estimator of zeta v for any v from 1 to n minus 1. Maybe this isn't the best estimator, but it is an unbiased one. Why we need v plus 1 is exactly for this issue that we needed, that Turing's formula only allowed us to estimate up to n minus 1. So we need a slightly larger sample size by 1 in order to get something unbiased. So for that reason, we needed a size v plus 1 sample. And then again, Turing's formula we've already seen is an unbiased estimator of zeta v. Now, we did this for one randomly chosen subsample, and well, we take another randomly chosen subsample, we also get an unbiased estimate of zeta v, get another one, we also get such an estimator. So what we consider is a eustatist.
You need v less than n only because you need a subsample.
Exactly.
Maybe you can use something like bootstrap to multiply your sample. If it's the only obstacle, maybe.
That is the obstacle. I'm not. That would be an I have not thought about using Bootstrap in this case. We are kind of still limited to the sample that we saw, so I would have to think about it. But that could be a very interesting approach. I would have to think about. Okay, so. Yeah, I think I already mentioned this. We could clearly consider looking at more subsamples. One way, of course, is some kind of bootstrapping approach, but we instead use a U-statistics approach, which means that we just consider every possible subsample. So there are n choose v plus 1 subsamples of size v plus 1. And this, so we just say, okay, well, we know that for every subsample, n1 for that subsample divided by v plus 1 is an unbiased estimator of zeta v. So we just average over all of the subsamples. And this is our estimator, which we call zv. Now, clearly, this is also an unbiased estimator of zeta v. And well, we can simplify it a little bit, right? Write out the combinatorial term, take out the v plus 1, and we can write it this way, where the sum is still taken over all of the subsamples of size v plus 1. And now, okay, so let's try to figure out what is this sum of n1 circle. Okay, sum of n1 circle. Well, this is still sum over all subsamples of, now this is just sum over all letters of the indicator of the letters we saw exactly once in the subsample. And, well, we can interchange summation. And what so we have sum over k, and this sum is sum over all subsamples. So this is saying how many subsamples have exactly one observation of letter k. And that's not difficult to compute. So again, this is, right, so the sum is the number of size v plus 1 subsets for which category k, or letter k, appears exactly once. Now, if v is less or equal to n minus yk, then, well, we need to, from the sample, from the number of species we saw with letter k, from yk we need to choose 1, and from the remaining letters that aren't letter k, we choose the remaining v observations. And then we can write out this combinatorial term in that way. On the other hand, if v is greater than or equal to n minus yk, that means that there does not exist any subsample with exactly one letter k. So the count is going to be 0. But either way, we can summarize this in terms of this formula here. I won't go through the details, we just transform this combinatorial term into this way, and we're multiplying things, there's some minus signs, and it turns out that when v is greater than n minus yk, this product eventually someplace will get a 0 here, and it will be 0. So no matter what happens, this is going to be exactly this summation. Yes?
What was Efron's contribution to this subject? He published a lot, but I have no idea.
Efron's contribution,
He published a lot on papers about the Turing problem, but maybe you have some idea.
I'm not sure. In what I've looked into Turing's formula, I haven't seen his work in it. I'm sure he's done some. Yeah, I have not looked at them, at least in the directions that I have been pursuing, sort of the ones I mentioned, the ones that have been relevant, but of course there's been a lot of work on Turing's formula, and I certainly am not familiar with all of the literature. Okay, so, right, so we are trying to get a nice formula for our estimator ZV, which we already argued is at least an unbiased estimator. And we saw that ZV can be written as this combinatorial term times the sum of n1 circle, which can be written in this way. And now we counted exactly how many ways we can do this. So now we just need to add them up over k. So that second summation, again, is just this formula. And now we just add up these formulas over k. And then we wind up with, after some simplification, we can write it in the first form, or after more simplification in the second form here. So now this gives us an unbiased estimator for zeta v for any v from 1 through n minus 1. And Zhao showed that this estimator is a UMV-UE for the Generalized Simpsons index v. And further, they showed a asymptotic normality of this form where sigma of v is a somewhat complicated function, so I didn't write it down here, but it can be written in a simple form, and it can be estimated so that we, in a consistent way, so that we still have convergence to a normal, and basically everything here we can write. Okay. So now I'd like to, let's see. Yeah, okay, still have. So now I'd like to talk about how we can use this to estimate other diversity indices, and perhaps the most well-known diversity index is Shannon's entropy. So Shannon introduced this index in 1948, and it's just sum of p, negative sum of pk log pk. If we think of it in terms of, again, a diversity index where we're weighting the probabilities, then now we can write this, right? We can bring the negative inside and write it as sum of pk log 1 over pk. And so now we're again kind of weighting small probabilities more than large probabilities, but now in kind of an unbounded way, whereas before, when we looked at the various Simpson's indices, the weights were kind of bounded. Here we're weighting it in an unbounded way. So if pk is really small, we weight it by really a lot. So this still gets to the idea of weighting the probabilities somehow and trying to look at the the smaller ones more. And again, we can use a plug-in estimator to estimate h hats, right? We can just plug in the pk's into the formula. And this is estimation, entropy estimation has been studied quite a lot. And of course, the plug-in estimator has been studied quite a lot, and it's been shown that it's asymptotically normal with given here sigma for finite k, and also Zan and Zan more recently showed that under additional conditions, this will also hold if k is infinite.
Again, maybe you know, was a big paper in analysis of probability by Coley Leonenko, who proposed, as people believe, the best empirical best estimation of entropy. Have you seen that?
I've seen his papers on estimation of Rene entropy, but not. But this is okay. What I can say is there are very many estimators of entropy that have been proposed. Many of them are kind of ad hoc, so that they work very nicely, but there's not too much known about their theoretical properties. Specifically, I know that Leonenko has worked on these kind of problems quite a bit, and I've seen his work on Rene entropy, but not on Shannon's entropy. Okay, and then Harris in 1975 derived the bias of, I guess the bias had been previously derived in the 50s, but they were using certain Taylor expansions that weren't, that didn't really converge. So they already had some idea of what the bias behaved like. But Harris, 1975, as far as I know, is the first one to really rigorously derive the bias of the plug-in estimator. And k, of course, is a number of categories. So this is only when k is finite. We only have a finite number of categories. And in that case, the bias decays like 1 over n. But when we look at this, we see a clear way that we can correct the bias, right? Because it's not too difficult to estimate this first term here. Now, if we know the number of categories, the number of letters, there's nothing even to estimate, right? We just plug in that value k. But in most situations, we don't know what k is. So we can estimate it just by saying,
What about Turing?
no, because this is so Turing estimates the probability of the total probability of unseen categories, but won't help us to estimate number of, at least not in a direct way, it won't help us to estimate number of unseen, the actual number of unseen species, only the sum of the probabilities of the unseen species. But we could just do it in, just take how many species we've observed thus far. And this is called the Miller-Maddow estimator after, well, Miller and Maddow, who, as they say, I'm not sure about Maddow, but Miller derived a formula similar to that back in the 1950s. It's just in a non-rigorous way using some Taylor expansions that didn't really converge. But basically, they already were aware of this, and so they proposed this bias-adjusted estimator called the Miller-Maddow estimator. But still, unless we actually know the number of species, there's going to be bias in p hat, and so it still decays on the order of 1 over n. Although in simulations, it's a very huge improvement over.
Better than the straightforward. In which sense is it better?
So it's at least trying to estimate the first term in the expansion.
N squared is better.
That's good. That's good.
Well, it's
One over n skilled, yes.
well, it's not really killed because there's still some bias in here.
The order is still 1 over n. So it's not
It's
still the same order.
It's not. It was not explained as a properties of k as an estimator of k. Maybe it's.
As far as I can see, they have the same order of error. So what sense the second is better? In which sense?
so I could say that k hat is not unbiased, which is why the order is still 1 over n. But it's even though there's still some bias, it's going to be better than just ignoring this term altogether. So the kind of the coefficient, instead of k minus 1, this will be something very small. There will still be something here.
Okay. So somehow he believes that also it will be better. Yes.
If the estimator is unbiased,
Or
it's
if
real.
you-
Yes. So it's so you can think of it, the expected value of this thing is going to be smaller than what you had initially. So that the coefficient in front of the 1 over 2, the 1 over n is going to be much, much smaller in this case than it was originally. And I will say in simulations, and I'll show some simulations in a couple of slides, Miller-Maddow works very, very well. Interestingly, Miller-Maddow even works well when we have an infinite number of categories. Okay, so these are the two most kind of classical estimators of entropy, although as I've mentioned, there's many other estimators of entropy beside these two that have appeared in the literature. Okay, so how is this related to what I've been discussing, to Turing's formula and estimation of Simpson's indices? Well, in a fairly direct way. Now, Shannon presented entropy in this way as a negative sum of pk's log pk's. But of course, we can take a Taylor expansion of the logarithm around 1. And when we do that, we can, and use Fubini's theorem to change the summations, we wind up that with...
Okay, what is the motivation? All probabilities cannot be around 1. Only one of them could be around 1. But all plenty of them. So why we spend all the terms around 0.1? Because only one probability we can believe may close to 1.
But of course, the Taylor expansion works with a radius of convergence 1, so it will still, it's just a different representation for the logarithm, but in our case, the motivation is that when we do this transformation, what happens is we have exactly a linear combination of generalized Simpson's indices.
Could they demonstrate somehow that this produce some better estimation?
That's what I'm going to hopefully present that I think that using, if we represent entropy in this way, what we've done now is we've written entropy in terms of a linear combination of generalized Simpson's indices. And we just discussed how to estimate generalized Simpson's indices up to order n-1 in an unbiased way. So what we have done is we've transformed the problem into basically, instead of kind of estimating this entropy, we're basically transforming the problem into estimating generalized Simpson's indices. And that's the motivation for looking at this representation. Now we can certainly do this representation because the radius of convergence is 1, so there's no issues with doing it. But what we get is we've represented entropy as a linear combination of generalized Simpson's indices, which is something that, at least for many of them, we know how to estimate.
But only for v less than n. So
Yes. Yes, exactly. Only for v less than n. So exactly that, of course. So we could divide it into the part we can estimate and the part we can't estimate. In other words, the part we can estimate and bias. Now, so we propose basically to estimate the first part, and we have an unbiased estimator of this first part, just as a linear combination of the generalized Simpsons, our estimators of the generalized Simpsons indices. Of course, we still have bias, and there's no way to get around bias. It's actually been proven that entropy cannot be estimated in an unbiased way, so we have to have some bias. But what can we say for the bias? Let's assume that we have a finite number of categories, and even for the plugin, really, this is the only case where bias is well understood. So our bias has this very explicit form, right? It's the sum of kind of this combination of Simpson's indices starting at n. We can interchange the two summations and write it in this form here. We can upper bound, get rid of the 1 over v upper bounded by 1 over n. Right, and rewrite our summation, and then by geometric series, this will just converge to 1 over pk, killing this 1 over pk here, and leaving this representation for the bias. And I mean, this representation for the bias is always an upper bound, or this is always an upper bound on the bias, even in the case where we have an infinite number of categories. But when we have a finite number of categories, we can clearly upper bound this by the sum by k, and the pk by the smallest pk that we have. And so we get this upper bound on the bias, which now decays exponentially fast. So if before we had decay like 1 over n, now we have decay that's exponential decay of the bias. Okay, so that gives us this this estimator, and we know it has exponentially decaying bias. So I'd like to theoretically, these seem like nice properties, but let's see how it actually does in simulations. And I will consider simulations based on 4 distributions. The first one I call triangular because, well, it looks like a triangle. Just basically k, normalized appropriately, where k goes from 1 to 100. Zip is basically 1 over k, again from 1 to 100. So the first 2 are situations where we have a finite and bounded support. 3 and 4 will have a unbounded support. So we have Poisson distribution, where for simplicity I took the mean to be E. And one that a very heavy-tailed distribution, basically like 1 over k squared. So let's see what happens with these 4 cases. Now, actually, this best one is an estimator I haven't discussed. I'll get to it. I'll say something about it in a moment. So the red line is from the MLE, or the plug-in estimator, which is not doing think, a very good job. The green line is the Miller-Maddow estimator, which seems to do really improves things a lot. The blue line is from this proposed estimator I mentioned, which maybe doesn't beat the Miller-Maddow estimator too much, but it's still doing a better job. And then there's different ways that we have looked at trying to modify. And maybe so. The nice thing about this estimator we've discussed is it's kind of has a simple structure, and we can easily get to its theoretical properties, and it has nice theoretical properties. It also has asymptotic normality, which I'll discuss in a little bit. So it has nice properties, but in finite samples, there's different ways to improve it. One is a jackknife approach, which I don't present here. Another is we have a paper where we tried to estimate the bias in some ways.
I'm missing. What explain again, please, the best, how the best estimation works?
Yeah. So the best one, I don't want to get into details as it's a little bit technical, but the idea roughly is we do the estimator, our estimator, and then we try to estimate the bias. We kind of know it decays exponentially fast, and we look at, we try to model it by kind of looking at smaller samples and getting an idea of how, and trying to estimate the bias from smaller subsamples, and we fit kind of a curve through that and add it. I didn't want to discuss this this modification here.
It's your method, or you?
It's my method. Well, my with Zan. But it's a little bit complicated. I didn't want to get into the details, but it's a way of taking this method and trying it kind of the way Miller-Maddow tries to estimate a little bit of the bias of the plug-in estimator. We try to estimate a little bit of the bias of our estimator and do this modification. We've also looked at other modifications like a jackknife modification, which also improves things quite a bit, but I'm not presenting that here. Mainly here, I just want to show that even without bias correction, the estimator is quite good. Here's for the ZIF distribution. So you see a similar situation. For the Poisson distribution, so of course for the Poisson distribution, we have actually an unbounded support. But still, one thing to note, Miller-Maddow, even though its motivation is just for finite support, still does a very, very good job in this case and beats the plug-in estimator by a lot. And then our estimator also does quite well, and bias-adjusted one as well. And then for this power decaying distribution, which has very heavy tails, again, and then unbounded support, again, we see similar situations. So in simulations, at least, it seems like a reasonable estimator, and it has nice theoretical properties that we can look at. Red is maximum likelihood, which is the plugin.
You have also some kind of theoretical background, like convergence or something. What kind of theory you have for your estimation? What kind of theoretical results?
So, well, we saw the theoretical bias, and
for your method.
For this method, we don't have. We just have for this one. We just have some heuristic ideas and simulations. So that's part of the reason I don't want to say too much about it. It seems to work well in practice, but we don't have the theory well developed for it. But this estimator, which is kind of modifying, we have a. Yeah, so that's why in this talk I'm really focusing on that one, but I'll just include this one here as well, just to show that there's ways to try and modify and improve it. But again, this is somewhat heuristic. Okay, let me see. I don't know if maybe this is a good point to take a break, and then we can continue and talk more. About other diversity indices and about asymptotic normality in some applications. Should we get started on the second half of the talk? Okay, so this approach. Yeah. So this approach we discussed with entropy we can do for a wide class of diversity indices. So most diversity indices, I don't know about most, but most of the ones that at least I have come across are either of this form or a simple transformation of this form, where we have sum over k, pk times some function f of pk, where we, at least in the notation of Patil and Talley 1982, we call f a measure of rarity. So again, it kind of, we think of it as a weight function that weights certain probabilities different from other probabilities. And this paper, Patil and Talley, I think is one of the, probably not the first, but it's kind of introduced a lot of approaches to thinking and talking about diversity in general, and they consider in particular families of diversity indices of this type. And now the approach we use with entropy, so long as f has a Taylor expansion around 1, with a radius of convergence at least 1, we can write any such diversity index, right? After some, playing around with Taylor expansions, as a linear combination of the generalized Simpson's indices. And in order for consistency, I use here when v equals 0, I write zeta v, but zeta v is nothing too fancy. Zeta v is, zeta 0 is nothing more than 1. So I don't think so we could just call it 1, but just for consistency here, I call it zeta 0. So basically, any such diversity index can be written as this kind of a linear combination of generalized Simpson's indices, where WVs are some kind of weights. And there's a lot of indices of this type. Of course, the generalized Simpson's indices, and Simpson's index in particular, is of this type. It's a very simple linear combination. It's just zeta v, but in particular, it's a linear combination. Shannon's entropy, as we've already seen, is of this form. So René's entropy isn't, but something we call René equivalent entropy, which we write as just sum of the pk's to the r for any r greater than or equal to 0, except, not equal to 0, just greater than 0, not equal to 1. Of course, that 1 is not very interesting. And in particular, this includes Simpson's, the other form of Simpson's index that we discussed earlier, that we were thinking about. And we'll use René's equivalent entropy a little bit later to derive some results about actual René's entropy, which I'll also discuss a little bit later. Emlin's index is also of this form, where we weight by an exponential function. And richness index it's a fancy name, but in ecological applications, that's just number of actual species that are observed. This also turns out to be of this form. It's just the sum of all of the generalized Simpson's indices. I think in the paper we have a number of other indices, but this is just some collection of indices that have been used in the literature that all have this form. And honestly, I'm not aware of any indices that aren't at least some kind of transformations of indices that are linear in the generalized Simpson's indices.
There was a classical GD index in economics. Is it also reduced to this? The number of people who have given portion of Commonwealth. What is the number of people who have, say, 60% or 40% of all national wealth? This kind of economical GD index.
Yeah, I'm not sure. As I said, I know that Simpson's index is sometimes called Gini-Simpson, but I guess that's a slightly different index. So I'm not sure about that one. I do remember reading about it. It's somewhat complicated. You have to integrate certain things. So it is a more complicated one. So that one I would not be sure about. Okay, and of course, again, we can estimate this with a plug-in estimator, and for many of these indices, the plug-in estimator is what's most commonly used in the literature. On the other hand, we can use the approach that we've just discussed for entropy, right? We write our linear diversity index as the part we can estimate from 0 to n minus 1. Plus some bias, which we can't estimate. And again, the first part we just estimate by taking the linear combination of these ZVs, which we derived earlier. We're assuming that the weights are known. They come from the particular form of the diversity index that we have chosen. Okay, and as with entropy, following basically the same kind of arguments, so if we have a finite number of letters, and if the WVs are bounded by some constant constant m, and this condition is true at least for all of these indices. Under that condition, using basically the same arguments that we used for entropy, we can show that the bias also decays exponentially fast.
What about Salis entropy? Have a look at Salis.
So Salis, although I don't talk about it here, Salis is a transformation of this Renyi equivalent one, and I'll talk about estimating Renyi, and the exact same approach can be used for Salis. But I don't discuss it specifically in this talk.
If pk decreases with n, then it's not any more exponential.
I'm sorry?
If pk decreases and minimum is near 0, and then 1 minus p also near 1, and 1 to the power n will be 1, and it will not to the exponential in the fast rate.
Yes. So in general, when we have an infinite number of categories, we don't have. I'm not claiming in that case that we will have exponential decay, and also I should say that in the case of just the plug-in estimator, I'm not sure that actually the bias has really been studied too well. Either, but yes, this is specifically I specify k is finite. If it's infinite, of course, we cannot say anything. We did see some simulations earlier in terms of entropy where we saw that even when we have infinite categories, it seems to do well, at least in the distributions that we looked at. Poisson and this kind of heavy-tailed distribution, 1 over k squared. But yes, I make no claims about the bias in the case of. I mean, we could write out the formula for the bias, but I make no claims that it will be exponentially decaying in that case. In fact, in general, as you say, if the pk is basically, I mean, this kind of trick of taking the minimum will not be there, and it will become 1, so it will not be exponential decay. Okay, so within this context of these linear diversity indices, I'd like to talk about asymptotic normality. I won't go through the whole proof, but I'd like to talk a little bit about how we can show asymptotic normality. And to do that, let me introduce slightly some additional notation. So let P star. So I'm going to be assuming that we have. So from now. For this part, let's assume k is finite. So we have a finite number of categories, in which case we have a finite vector of probabilities p1, p2, p3, all the way until pk. But let's ignore pk because pk is uniquely determined by all the previous p's, so we don't need to worry about it. So let p star be our probability up to pk minus 1, but we're not going to include pk. And then p hat star will be our estimates of the probabilities of these parts. And again, we're excluding the estimate of pk. In which case, in this case, the probability all of our, the vector of all probabilities is basically all the values coming from P star. So I'm just thinking of it, take the elements of P star here, followed at the end by 1 minus the sum of all these PIs. That's the whole distribution, but we're just ignoring the last term, both in the distribution and in the vector of estimates. And we'll see why we want to do that in a moment. Let sigma of P star be the covariance matrix of P hat star. Now, of course, it's the covariance matrix of P hat star, but the reason I put here P star is, of course, the covariance matrix of P hat star is a function of just P star. And we can, I don't want to write messy formulas here. We can write it's not difficult to write down what this covariance matrix looks like. It just looks a little ugly, but easy to write down, and basically well known. And let G of P star be the gradient of theta P star. So vector of partial derivatives of our index. Remember our index theta is of this form, so we're looking at the gradient of this. But again, keep in mind that for the last term is really a function of all of the p's. So theta, which is sum from k equals 1 through k minus 1, pk times f of pk, plus 1 minus sum from k equals 1 through k, capital K minus 1, pk times, times f of 1 minus sum from k equals 1 through capital K minus 1, pk. So it's so we have pk's is in one term of this sum for a particular k. It's in one term of this sum, or let me say pj is in one term of this sum, but also in both of these parts. So when we take the gradient, we need to take into account that it's in both of these. So we call this this gradient G of P star. Okay, so now to derive the asymptotic normality, actually first, before deriving asymptotic normality for the estimator that we're proposing, I will derive it for the plug-in estimator, and we'll use that to derive it for our estimator as well. So first, pretty in the straightforward way, from the multivariate normal approximation to the multinomial distribution, we can show that this vector of p hat star minus the true probabilities, again leaving the last term out, times root n converges in distribution to a normal with mean 0 and sigma and covariance matrix exactly sigma of p star. And so the reason we wanted to initially get rid of that last term pk is that now this multivariate normal distribution that we're converging to is in fact a full normal distribution. It's really k minus 1 dimensional. Otherwise, it would be would look kind of like it's a k dimensional, but would really be on some k minus 1 dimensional subspace. So we would have a covariance matrix that's non-negative definite, but not a positive definite, whereas here we're guaranteed that this covariance matrix is positive definite because we got rid of kind of that constraint that the probabilities have to add up to 1. Okay, and very simply by the delta method, from here we can get convergence of the plugin for theta, just written in this way. Write this.
Theta is vector or scalar?
Theta is scalar, right? Theta is this object. Yes. So theta is scalar. Of course, we have to kind of multiply by this this term here raised to the minus 1/2, right? Which is our covariance term, which is this is our covariance matrix times the gradient transposed gradient, so this is also going to be a scalar
That's
term.
a Taylor expansion.
Yeah, exactly. So just standard application of the delta method. And further, what we can say is, because we could say, well, how useful is this, since it's still, we need to know the p stars, but we can estimate p star by p star hats, and since we know that p star hat is a consistent excuse me, a consistent estimator of p star, then by the continuous mapping theorem and Slutsky's theorem, it's clear that this will still converge to normal 0, 1. But now everything here, right, we can estimate, we can plug things in so that we don't need to know anything about the distribution, the true distribution, in order to figure out, to estimate things that are on this side here. And of course, from this, we can do some kind of asymptotic confidence intervals or asymptotic hypothesis tests. Okay. And now we'd like to get, I'm sorry, I didn't...
What will sharp on total?
Yes, give me 1 second, I'll come to that. But first, there's one important point I didn't mention. Of course, for this to be true, we need this thing to not be 0. So I wrote it up there. G of p, or it should be p star, should not be 0, right? Since we know that this is a positive definite matrix, right? Specifically, we left out that last pk term in order to guarantee that sigma was a positive definite matrix. In order for this whole term to not be 0, we need g of p to not be 0. And in various situations, it's not hard to check that, and in fact, well, I'll give a simpler condition for certain situations in a little bit. So yeah, that's a point that I wanted to emphasize. And now let's. So I don't think I used this notation earlier, but theta hat sharp is my notation for this estimator that we introduced based on generalized Simpson's indices. Oh, I didn't use this notation, right? So this is our estimator based on Simpson's estimating the first n-1 Simpson's indices. So for this estimator that we're proposing, now we'd also like to get asymptotic normality, and yeah. So and we do under the exact same conditions. Right, we just need g of p star not equal to 0, and so long as we have that condition satisfied, then this is the exact same statement we had for the plug-in estimator. That's this theta hat star minus theta in this normalization converges to a standard normal, and again we can estimate p star by p hat star. And now we get something on this side. Everything doesn't require knowledge of the distribution. So the exact same result we get for this sharp estimator. And I don't want to get into the details of the proof. It's a bit technical, but I do want to say what the basic idea, how we prove this. So the way we prove this is very simple. We look at root n times theta hat sharp minus theta, and we add and subtract theta hat, the plug-in estimator, right? Theta hat is our plug-in estimator. We add it and subtract it. Now we know that this term here approaches the normal distribution, and the right normal converges to a particular normal distribution, and then with some standard deviation, which later we could divide by. And so all we need to do is show that this first part converges in probability to 0. Once we've done that, we've established the asymptotic normality. This step, as I say, it's a bit technical, so I'm not going to get into all of the details here, but this is the basic idea of how we prove this. And maybe one thing to mention here is, in particular, a very good kind of, entropy is a very good example of this kind of linear index. And so this result in particular holds for entropy, which we already discussed separately, but not its asymptotic normality, because the asymptotic normality comes exactly from this theorem. And the interesting thing is for entropy, that condition g of p star not equal to 0 can be written as
This is applicable to any entropy, renew included or renew anything. Whatever.
it's not directly applicable to Tsallis because it's not, so it's only to these kind of linear indices, but it is, but Tsallis is a transformation, and Renyi is a transformation of ones of this form. And, yeah, and I will discuss that in just one or two slides. But what I do want to say is, for Shannon's entropy, the condition g of p star not equal to 0 is equivalent to the condition that basically that we don't have a uniform distribution, so that
For uniform will be 0, yes.
yeah. So pi is not equal to 1 over k for at least one I in 1, 2 through k. So this is just a fancy way of saying it's not the discrete uniform distribution. So long as it's not uniform, the asymptotic normality holds for Shannon's entropy. And of course, for the plug-in estimator, that's the fact that so long as this condition holds, we get asymptotic normality. That's been known for a long time, but here we extend the result to this new estimator, theta hat sharp. Okay. Yeah, so now I want to talk a little bit about estimating René's entropy, which is not itself a linear diversity index. It can't be written as this kind of a sum that we've been focusing on. It's written as the logarithm of such a sum times 1 over 1 minus r, and this is René's entropy of order r. This is true for any r greater than 0, r not equal to 1. But if we take r approaching 1, René's entropy approaches Shannon's entropy. So we kind of think of Shannon's entropy as a special case of René's entropy when r equals 1. So this is this is one of the most commonly used indices in at least in ecological applications, either this or a slightly different transformation of the sum of pk to the r, which also, as r approaches 1, approaches Shannon's entropy, which is Tsallis entropy. So I only talk about René's entropy, but the approach will be very similar. We just have a slightly different function of this sum. Otherwise, everything is basically the same in that situation. And so again, we see that in this case we have basically anything depending on the pKs is just summarized by HR, which we called René equivalent entropy earlier. And the reason we called it that is because in some sense up to a simple transformation, it's exactly just HR. And of course, we can get asymptotic normality for René's entropy by applying the delta method one more time. So yeah, this is just repeating what I just said. So yeah, so now we can apply. So what we could do, we can estimate René's entropy of order r with just plugging in our entropy, our estimator of René equivalent entropy into here and taking the transform of that. Now, of course, this will have major effects on the bias, but in terms of asymptotic normality, by applying the delta method, it turns out now we need to add this term here, where HR is exactly our estimator. I'm sorry, this should be, oh, no, yeah, this is HR, this is the true, this is the true value of Rene equivalent entropy, but basically using the delta method one more time, we get this asymptotic result. And again, everything here on this side can be estimated. We can estimate this with HR hat sharp and these P stars with P hat stars. So everything here can be estimated and in a yes, all of this at this point is for finite categories. Yes, we assume that we don't know how many categories, but we assume that it's finite. We haven't looked at the infinite case, though I will say that even for entropy, in terms of the plugin of entropy, the infinite case wasn't known until quite recently. But definitely that's an interesting question of what happens with infinite categories, and one I think that's worth thinking about, but we don't have those results yet. Yes, this is just for finite categories. And again, we have the same condition, right? We need G of P star not equal to 0. And as with entropy, in the case of Rene entropy, that's equivalent to not having a uniform distribution. So long as it's not uniform, the result will hold. Okay, so that's a little bit about at least our approach to estimating various diversity indices. I've talked about a lot of different diversity indices, and I want to say maybe a little bit about how do we think about diversity indices, and in some sense, how do we choose which diversity index we want to work with. And so I will discuss kind of two approaches. The first is based on majorization theory. I already talked a little bit about majorization theory last week, but I'll try not to repeat myself too much, but I'll just talk a little bit about majorization theory in the context of diversity indices. And then I'll talk about a different way of thinking about things in terms of thinking about weighting the probabilities in different ways. So very, very briefly, I'll review majorization theory. And so if we have two distributions on a finite alphabet, P and Q, let's write P sub with square brackets to be the elements of P in order from largest to smallest. And we can do the same thing for Q. And then we write that P is majorized by Q if this inequality holds for every K. So that means that the largest value of P is smaller than the largest value of Q. The sum of the sort of first two largest values of P are less or equal to the sum of the first two largest values of Q, and so forth. Of course, when we add them all together, since these are probability distributions, they have to add up to 1. In the previous talk, we had a different condition here because we weren't just talking about probability distributions, but of course for probability distributions at K, they have to equal 1. But we still have this inequality that we think about. I've already talked a lot about how majorization is related to diversification, but one thing I want to emphasize is that the uniform distribution is majorized by any distribution, and in particular, at the very least, kind of we could think of uniform as being the most diversified distribution. So that is something that people in ecology really like to see, that that uniform is the most diversified. And so that gives us maybe some intuition that we might want to think of P as being more diversified than Q if P is majorized by Q. I want to give a second intuition, which I also discussed last time, but I guess this is the one that really helps me to think about this. So if we have some distribution Q, and we take a little bit of probability mass from its most probable, the one the letter with the highest probability. We take a little bit and we add it to the letter or species with the smallest probability. But we do this in a way that doesn't change the order of the probabilities, but just makes this one little modification, and we denote this new vector p. I think intuitively we can think that p should be more diversified than q, and it's very easy to show from the definition that p in fact is majorized by q. So maybe that's a little bit more intuition as to why we think that if p is majorized by q, then p is somehow more diverse. Okay. Now I'll define, and again I defined these functions last time in maybe a little more generality, but let f be a function basically from 0, 1, and to r, such that f of p for any probability distributions p and q, I wrote here from f from 0, 1 to the power n, which is fine, we can write it that way, but in this case I'm really thinking of it from the collection of all probability distributions, which of course have additional constraints.
But I just want forgot what is the convex function is the sure concave on this
So
you have convex function, it is enough to have.
Convex, so is a convex function enough to be
Sure
convex?
Sure. How they are related?
I think maybe on the next slide I will. So it's
Just convex, classical sense, and sure convex.
I believe convex. I mean, in general, in the sense of RD, it should imply sure convex, but not the other way around.
Convex should be more than sufficient.
No. There's a relationship in one way. I'm forgetting exactly which one. But yeah. I believe sure convex implies convex, but not the other way around. But I would have to double check that.
Yeah, well, my intuition is that convex should be sufficient. Sure or not?
I'm not sure. I'd have to look it up and think about it. Okay, so we say that a function is sure convex if f of p is always smaller than f of q whenever p is majorized by q. And conversely, we say that a function is sure concave if f of p is always greater than or equal to f of q if p is majorized by q. Now, since we're thinking of p, if p is majorized by q, we think of p as being more diverse, we'd like the diversity index to be bigger for p than for q. So we'd like a diversity index to satisfy to be sure concave. And that's a condition that sometimes people in ecology like to impose on a diversity index. And in this case, in the ecology literature, they say that such a function satisfies the evenness property. Evenness property comes from this fact that the most diverse vector in this case will be the one where the probabilities are all even. And in ecology, they consider that to be a very important condition. Okay. What is true is that for any linear diversity index, of course, it can be written as this sum of pk, f of pk. And then this is going to be sure, a function of this form is sure concave so long as t times f of t is a concave function. And of course, if f is differentiable, twice differentiable, which, since we're assuming it has a Taylor expansion, it's going to be twice differentiable. That condition is equivalent to 2 times f prime plus t f double prime is always less or equal to 0. So that's a condition. So that's the condition on the kind of weight function that we need to impose if we want our linear diversity index to be sure concave. It's easy to show that Shannon's entropy and René's entropy are sure concave. We can also show that Simpson's index, the regular Simpson's index, is sure concave. But it turns out that the generalized Simpson's indices for k greater than or equal to 2 is not sure concave. So, they don't have this property, which on the one hand might make us think, well, maybe they're not good diversity indices. On the other hand, I think we can interpret them in a different way, and even though they don't have this property, I do think that they have some, there's still something to using them. And to talk about that, let me talk about this other way of thinking about how to choose a diversity index based on trying to weight different probabilities in different ways. Right? So consider this is a slightly more general version, general index than the generalized Simpson's indices I've discussed. Actually, in the paper by Zhang and Zhao, they consider this more general class as well, but I haven't discussed it. And we can use the tools that we were talking about. We can write a Taylor expansion of this in the right way, that we can still use all of the methodology we've been discussing for estimating these kind of more general Simpson's indices. But what we could think of, if we have an index of this form, what we could think of is, in some sense, when U is large, that tends to weight large probabilities more. And when V is large, that tends to weight small probabilities more. And so we could think, well, what do we want to weight more? So maybe we want to say that for us, it's a more diverse ecosystem if it has a lot of, there might be some species that are very common, but maybe we're interested in the ecosystem having more species that have smaller probabilities. And for us, that's an important issue. Then we might want to say, well, let's take U to be small and V to be large. So although this might not satisfy or will not satisfy the evenness property, depending on how we want to look at things, I think this could still be a useful and interesting way to talk about diversity.
Sure concave implies usual concave.
Okay.
Okay, thank you. And of course, we don't have to just, so I think it's very explicit in this kind of generalized Simpson's index to think about how we're weighting things. But in general, we can think about this function that we're multiplying by, right, this f of pk, and think about how it weights things and try to find one that we think weights things in the way we're looking at it. So again, entropy weights small probabilities by a lot. And if we really want to emphasize small probabilities, and entropy is a good way of doing that. Of course, entropy also has the nice property that it's also sure concave. But even aside for that, if we think of it just in terms of weighting small probabilities, I think it's a very natural way to do things and to do that. Okay, so that's what I was just discussing. And now I want to discuss an application. Let's see how much time I have. Okay, so still have some time. So I'd like to discuss an application to linguistics, and in particular to authorship attribution. So in 1985, the following poem was discovered. Well, it's not a very long poem. It's about 9 stanzas, but it starts, "Shall I die, shall I fly?" and keeps going. And when this was discovered, what it was written as the author of this poem, it said William Shakespeare. And before 1985, nobody was aware of the existence of this poem. And in 1986, it was added to the Oxford edition of the complete works of William Shakespeare. Partly, I think, because the editor of this was the person who discovered the poem. And so now it was kind of considered, I mean, this is one of the most famous complete works of Shakespeare. It's really considered whatever is canonical is there. I think they call it a song in the complete works. But this was a very controversial decision, and plenty of other people said, no, we don't really believe this was actually written by William Shakespeare. So it's an interesting question. Did Shakespeare really write this poem? And many literary scholars have debated this question, looking at it and saying, well, this looks like Shakespeare, or it doesn't look like Shakespeare, or some have said this poem is amazing, and others have said it's not a very good poem. I'm not going to sort of discuss my opinion on that, but I will add that some statisticians have also found this to be a very interesting question, and it was analyzed by Thisted and Efron in 1987, and Zhang and Huang analyzed it in 2007 from slightly different perspectives, but in terms of statistical analysis to see, is this really consistent with this being a work of William Shakespeare? And now I'd like to discuss a little bit of how we can use entropy to try and talk about authorship attribution. So in this context, our letters, ln, are just different words in the language. Shakespeare was writing in English, so let's say different words in the English language, including, Shakespeare also made some words up, so let's include words that he could have made up as well. And let Pn be the probability with which a particular author uses word el saben. Now, what we're interested in is figuring out, well, what is this this vector of Pn's, the probability for a particular author to use particular words, and to see if for different works, it seems to be the same probability distribution. Of course, I guess it's possible two authors have the same probability distribution, but in which case, of course, these kind of approaches will not work, but I don't think that's very, very common for that to happen, so I don't think we need to worry about that. But this kind of vector, it's a huge vector. I guess you could probably assume that it's even infinite if we allow for words that aren't real words. Or that aren't real words yet until Shakespeare started using them. So we want to try to summarize this distribution in some way, and the natural way to do it is in terms of some diversity index, because we could think, well, there's a different diversity to how authors use different words. Some authors tend to mostly use the same words, and other authors, especially Shakespeare, was quite known for using pretty diverse words and even making words up when he wasn't happy with what was available. So we can summarize the information in terms of, for instance, entropy or...
But my understanding is that the real statistical analysis will be based on conditions of the sequence, not on individual words, but on the sequence, on Markov chain kind of an analysis. And I think that actually people to discuss not just frequencies mostly, but the chain of
yes,
in this context.
Yes, so that's certainly something that has been done and looked at for authorship attribution studies. That's
experience as well.
Yes, for analyzing Shakespeare and a lot of other works. That's not the approach that we're using here, but that's certainly a very common approach. I think maybe even goes back to Kolmogorov.
Yes, of course.
So definitely.
Even to Markov.
Oh yes, yes, to Markov.
Yes.
Yes.
The first tables. He invented Markov chains, by the way, by analyzing Evgeny Onegin. He created the table which word follow which frequencies in Onegin. Okay, but this is the story. Нет, вроде бы это правда так. Вчера все правда.
Yeah, so that's definitely that's a popular approach. That's not the approach that we use here. We just use the approach of just looking at frequencies. But of course, there's different ways to do it, and certainly that's a very common one. But we used this approach.
Based on complexity and so on.
Oh, okay, so I believe that really discussion about authorship they are not only about frequencies, about also sequences.
Blocks.
Yeah, so there's certainly lots of works in that way. There's lots of works in several directions. So I've certainly seen that approach. This is a different approach where we just consider the frequencies themselves, but certainly there's many ways to do this. Okay, so in this case, right, we say let's just compare the entropies of the authors and see if we could estimate the authorship of, say, the poem we just looked at with some authorship of Shakespeare's other work and try to compare their entropy. And that's certainly one way to get at authorship, but of course there's many different ways to do it.
But Shakespeare used 5,000, so how many works?
I don't know, I mean, that's certainly been studied.
Numbers in my book, the real numbers. I give you numbers, check it. That's real and they're taken from. Okay. You can read all these numbers here. All the numbers.
Yeah.
Есть большая дискуссия насчет того, как считали до тех водонов. Там не сходятся.
Фоменко, да, это делал?
Ну и другие люди, там действительно не сходятся. Да.
С кем не сходится?
Ну вот, например, с каким-нибудь там, с любой человеком, там каким-нибудь там, абсолютно другая статистика.
Нет, вдруг это гениальный человек просто, он может так писать, а может так специально.
Yeah, I don't think we have too much time, so let's maybe try to finish at least this example. Okay, so of course we've had this nice discussion. There's definitely many ways to do this, but the way we are discussing here is that we can compare the entropy of a corpus of an author's known work with the work that whose authorship is in question. In particular, we compared Shakespeare's sonnets and took that as the corpus to compare with this poem. And part of the reason for that is exactly, I think, this issue that you were discussing, that authors may write in different ways when they're writing different types of literature. And certainly writing a play like Macbeth or Hamlet is very different from writing a poem. So for that reason, we wanted to specifically focus on Shakespeare's poetry. And so we looked at the sonnets. So our corpus is all of the sonnets without the names, which I think are not really official. Most of them are just usually they're either numbered or the first line is the name. So we didn't include any of that. We just looked at all of the sonnets and took that as the corpus. And then the way we proceeded is first, so at least one way that we can proceed is to estimate the entropy of the proposed text and that of the corpus. And we know we have some asymptotic normality, which suggests we could perform a two-sample z-test. However, we found that there was some difficulty in doing a two-sample z-test. And we suspect it's related to the fact that we're estimating things with with very different amounts of bias. The poem has, I forget, 400 some words, and of course Shakespeare's sonnet has much more words. And so the amount of bias in our estimates of entropy is very different in the two cases. And so when we looked at the difference, kind of z1 minus z2 divided appropriately, this difference, it seemed that part of the problem was that we had a lot of different bias here. And we compared with the things that we knew were Shakespeare's and so forth, and we were getting a lot of problems with doing this two-sample z-test, which we think is due to the fact that we're subtracting things, but they have unequal bias. If they had similar bias, the bias would kind of cancel out. But even under the null hypothesis, they have very different amounts of bias. So that was causing us trouble with using a two-sample z-test. So instead, we considered a rank test. So what we did is we took the corpus and kind of chopped it up into smaller pieces of length equal to the length of the poem. And then we estimated the entropy of all of these pieces along with the entropy of the poem, and basically we ordered them from smallest entropy to largest entropy. And if the entropy of the poem is very, very much in the tails, then that's kind of evidence against it. And basically the p-value is the probability of seeing the poem in as far away from the center as it is, or even further away. So that was our approach that we used for this problem. This just summarizes what I said. So, and then we compared the poem. So we didn't just compare with Shall I Die? We wanted to see how well this methodology would work in other situations. So we took a poem, The Phoenix and the Turtle, written by Shakespeare. At least everyone seems to agree it was written by Shakespeare. It's not a sonnet, so it wasn't in the corpus, but it's a poem, so it's not a play. It's a separate poem, and we compared with this poem. We also took 4 sonnets by Philip Sidney, who is a contemporary of Shakespeare's, just to see how well that would work. And then, of course, we looked at Shall I Die? And so here's what we found. For The Phoenix and the Turtle, the p-value was 0.36, which is good. It means we can't reject. And, of course, we know that's written by Shakespeare. For the 4 sonnets by Philip Sidney, we found p-value of 0.02. So
the entropy of Sidney is smaller.
Well, this is the p-value. I don't remember if it was smaller or larger, but it was quite far away from the entropy we saw with Shakespeare. But I don't remember whether it's smaller or larger. And then finally, for Shall I Die? Well, we got maybe not the most convincing result. We kind of got a marginal result, p-value of 0.09, which is exactly where you're kind of not sure whether you want to accept or reject. So I guess on the one hand, you could say, well, maybe we didn't really answer the question, although very much, because still this is a kind of marginal and you don't know what to do with it. On the other hand, I kind of think maybe for certain problems, we don't know, right? We need to interpret what we get, and maybe in this case, with a poem like this, maybe it's in some ways. I mean, if all of the experts in Shakespeare cannot agree, perhaps it makes sense that we would have, a statistical analysis also would be somewhat inconclusive. So that's what we found with this poem. I think in the paper we argued a little bit that it's maybe more likely that it's not by Shakespeare, but I'm not so sure. I think maybe sometimes you should just leave a marginal result as that. We still don't know, but at least the methodology gave good results for showing that a poem of Shakespeare was by Shakespeare, or at least we couldn't reject it was by Shakespeare, and rejected quite easily the sonnets of Philip Sidney.
And what are the results of Markov chain analysis? Again, you concluded, I think, about this problem.
So I am not sure. I think that this paper by Thisted and Efron, I believe, did some kind of Markov chain analysis, but I think that they didn't reject, but they were comparing with all of Shakespeare's work. Yes, which. I think that's. Definitely you have things in there that are quite different from, I do think that, although of course he wrote his plays in poem and in lyric, but still I think it would be quite different. So, but with just the sonnets, that analysis hasn't been repeated. I should say that paper of Zan, who's my collaborator also on this work, they used Turing's formula directly, and if I remember correctly, they found that the poem Shall I Die has, I think, 9 words that were not used anywhere in Shakespeare, and based on asymptotic normality of Turing's formula, they rejected based on that analysis.
Too many.
Yeah, too many. I think 7 was the amount that 7 would have been okay, but more than that was too many. Yeah.
So I understand there exist many other approaches how to check authorship attribution. One that I know is based on change point techniques. So you put 2 text, one and the next one, and you believe that the first text belongs to Shakespeare, the second you are hesitating, and then you simply analyze the distribution of words, or maybe the distribution of letters, for instance, in some window. And then if after changing the text, the distribution has been changed, then it means that this text have different authors. And there is another approach which I heard from Malutov and Kokhlov that we can analyze in terms of mutual information. So create some statistical tests and then analyze it. So is it possible to compare these different approaches? Did you make...
We did not compare with other approaches, but there's many approaches. I think just here today, you mentioned a couple, and Professor Kelbert mentioned a couple, I mentioned a couple, so there's a lot of different approaches. We did not compare different ones. As I said, I know of at least 3 papers that have specifically analyzed this poem in different ways, and at least reached somewhat different conclusions. The paper of Thisted and Efron didn't reject. The paper of Zhang and I think Huang did reject, and we kind of got intermediate results. But there's definitely many other approaches that could have been performed, but as far as I know, haven't been done on this poem.
This topic is very popular today because of this plagiat history. What appeared in Germany as well as in Russia, that some PhD dissertations are not written by the persons who defended them.
Oh, really? I haven't heard of that.
And as I know, there is one...
So there's a big sort of issue with that?
Maybe not one, many computer programs, but one of these programs is popular in Russia, and through this program you can check whether this work was not copied, Ctrl-C, Ctrl-V from other works.
Mm-hmm. Yeah, I mean, that I certainly heard for various term papers. I didn't know that the issue went all the way to PhD dissertations. But yeah, I know there's definitely a lot of work on that, I guess, probably in information theory and computer science. I guess the approaches here come more from the linguistics literature, and they're using these kind of indices is something that they do quite a lot of, usually using things more like the plug-in estimator than the estimators that I've been discussing, but and not worrying too much about their theoretical properties. But this seems to be the approach in a lot of the quantitative linguistics literature. I would guess for in the kind of engineering, computer science literature, probably do things more kind of information theory based. Okay, I guess I'm getting kind of toward the end of my talk. I do want to say a little bit about some extensions without really getting into the details of them. So one thing we also considered estimating Kullback-Leibler divergence between 2 independent distributions, which is just this form here. And we considered estimating mutual information, which is actually a particular type of Kullback-Leibler divergence. It's the sum over k, and we have 2 random variables x and y on the same on 2 alphabets, not necessarily the same alphabet. And here we have their joint distribution, so p of x.
This is between products and zero distribution. You don't need to write it.
Yes. Yes, it's a Kullback-Leibler divergence between the joint distribution and the product distribution. Exactly. Yes. So it's a type of Kullback-Leibler divergence, although we need slightly different tools for analyzing them, because for Kullback-Leibler divergence, we assume that our samples are independent, and of course they're not going to be independent for mutual information, and especially for the variance, it's going to be quite different in the 2 situations. But we also considered such extensions, and I want to say maybe a little bit, I don't want to get into the details of the estimators, but I want to maybe say a little bit about how the estimators work. So this is specifically for Kullback-Leibler divergence in some simulations we made, and we compared, so this is the divergence between 2 distributions, 2 kind of triangular distributions. One is pk equals 100 minus k over 50/50 for k equals 1 to 0 up through 99. And the other one is 100 minus 0.5k divided by a slightly different normalizing constant, 75, 25. So these are the two distributions. We looked at other ones, but here I'm just presenting what we saw for comparing these two distributions. And so this is P, this is Q. And so in the first case, we are estimating the Kullback-Leibler divergence between the distribution P and the distribution Q. This dashed line is the plug-in estimator, and the absolute bias of the plug-in estimator, which is quite large. And the dark line is our proposed estimator based on similar techniques that we've discussed for entropy. I don't want to discuss all of the details. It's very similar, some differences for our estimator. The fact that we can write Kullback-Leibler divergence as kind of a difference of two parts actually helps to eliminate some of the bias. So actually the two parts kind of work together, so we wind up getting less bias than for kind of estimating each part separately. And so this is what we see for the bias, at least in our simulations in this case. And then we also wanted to see, since we can estimate standard deviations, we can build some asymptotic confidence intervals. We want to see how well they work. And so we had, I think these were 95% confidence intervals, and we wanted to see what the coverage actually was. So what percent of the observations actually fit into our sample confidence interval. And so this is for our estimator. And the sample so we see it's pretty close to what it should be, about 95% for our confidence, asymptotic confidence intervals, whereas for the plugin, it's really bad. And I think the reason it's really bad is that the plugin has more bias, and when we have the confidence interval is an asymptotic interval. So when we use it for a finite size, it kind of winds up being too small, and actually the bias winds up being more so than this very small confidence interval. And so that's why we think that the problems are with just a plug-in estimator. Okay, so this is what I wanted to kind of give these results for Kullback-Leibler divergence. For mutual information, I think it's something which well, it seems like people here know it quite well, but I know a lot of people don't really, they're aware of what it is, but don't really use it too much in applications. And I think it's actually a very useful thing, because the way we usually measure the relationship between two random variables is correlation. But we know correlation, now correlation being large, tells us a lot about the dependence. But if the correlation is 0, that tells us nothing. It doesn't give us any evidence that there's no dependence. But the interesting thing about mutual information is that it's 0 if and only if the random variables are actually independent. And so if we want to get to actually testing any kind of independence, using correlation is useless. Correlation is very important for, if you want to figure out what the trend is, for modeling doing a linear model. Correlation is very important. But if we just want to test whether we have dependence or not, basing it on correlation is not very useful, right? So, here's some simulated data, and we could clearly see that the first one is not independent, right? So this is x plotted versus y. So we just simulated random variable x and random variable y, and I plotted the value of x versus the value of y. Well, here clearly there's not independence. And of course we'll have a pretty large correlation here. Here, however, if we look at this, it's maybe less clear. Even when we look at it, looks a little bit strange. We might say, I'm not sure it doesn't look completely independent. There's certain things going on here, but on the other hand, there's a lot of spread here. You might think, well, maybe this could be independent, and certainly if we looked at the correlation, it would be very small. But actually, it's not independent. Independence looks more like this third picture. But if we looked at just correlation, here's what we would find. So these are the estimated correlations for the three pictures. In the first one, it's 0.7, quite large, and it's clear that it should be. But the second and third, they have a correlation very close to zero and very similar correlations. So if we were just thinking in terms of correlation, we'd say, yeah, they're probably independent. But if we look in terms of mutual information, now, okay, technically mutual information can't be negative, but unfortunately one of the properties of our estimator, although I think it's a very good estimator, but it can be negative when things are small, but that's, if anything, just suggests that it should be very close to zero. Of course, we could correct it and say, let's take mutual information to be zero whenever we get a negative estimate, but we don't do that. So if we look in terms of mutual information, well, the mutual information for B is actually really large, even larger than for A. So it seems to be capturing, there's actually a lot of dependence in the second one. It's just not really clear to the eye. I mean, you could sort of see, yeah, there might be some dependence. There's some kind of things around the edges suggesting dependence, but it's not clear. And correlation picks up nothing, but mutual information picks it up very well. So I think mutual information is actually something that maybe should be used more. I think usually it's used for some kind of theoretical results, but in terms of hypothesis testing, I don't think it's used much. And I think that especially if you're interested in independence, it's a very nice measure. Now let me tell you how I actually simulated these. So A is just x plus epsilon. Y is sine of ex plus epsilon, so again, very strong dependence, even if it's not completely evident in the picture. And y is just, here it's independent, so it's just epsilon. And
it's clear that it's sine.
Yeah, you can.
After this formula.
Yeah. Yeah, I put in, if you don't put the e in, then you really can see the sign. So I put the e in just to make it a little bit more messy. And the distributions here, where's my marker? X and epsilon are IID, discrete, uniform on, I don't think I included 0, 1, 2, up to 10. So those are the distributions for x and epsilon that I used. And so we see kind of the effect of that. Okay, so coming to the end, I want to say that the formulas I presented are somewhat complicated, but we have a package called Entropy Estimation, which is available on CRAN, which basically allows us, has all of these estimators in it for all of those. For most of the things that I talked about, and as well as estimators for the standard deviation, so we can do confidence intervals and things like that. I'd want to mention this package was written jointly with me and my wife, Li Juan Chao, and so that's available on CRAN. These are some of the references. I made reference to a lot of other papers, but this is mainly, I guess, my work in this, as well as some directly related work. So I'd be happy to take any questions. Yes.
It seems that this part of your course is quite good for, say, master programs or something like this, because I think that it's understandable for master level students.
Oh, okay. Yeah. Yeah. This is more kind of, you could see what's going on. There's less technical proofs here.
Why did you decide to publish your paper in the journal Neural Computations?
I guess my collaborator Zan had published several papers with them. It's a pretty good journal there, and they're interested in a lot of tools from information theory for studying kind of well, like brain imaging kind of
What you
things.
can say about estimation of mutual entropy in continuous context?
So that's something we're working on to extend our results to the continuous context. We think there's some kind of we're thinking of it in terms of kind of discretization, but we have not worked on that.
No,
But
okay, it's more tricky. It's not just
yeah, I know that it's not a direct. Certainly, it's not just directly transformable, but I think there are tools for looking at it from that perspective. So we have not.
Okay, what is more or less known in the literature?
There's a lot of various techniques, as with estimating all of these tools. Estimating all of these quantities. There's a lot of things, a lot of various approaches.
What do you like?
So I've mainly focused on the alphabet, so I'm not that familiar with the literature. I think that Leonenko actually has a very nice paper for estimating Rene entropy, which he does both for discrete and continuous, and he actually does some kind of a discretization scheme for the continuous case. This was published, I think. He has several papers in this direction, but the one I'm talking about was published in multivariate analysis. I know he has some papers on that in analytical statistics, but the one that I really, I guess the reason it's influenced me so much is because he also considered the discrete case, and that's the case that I tend to work in. But yes, he has a lot of very nice papers. But there's the literature is vast, both in the statistics and in engineering. A lot of ad hoc approaches. Most do not work very well in simulation, but do not have very much theory behind them. So what I like about our approach is that you could see kind of the underlying theory and where we get everything, as opposed to a lot of times it's kind of, it's a Bayesian approach, and they just try various priors until they get something that seems to work very well. So there's a lot of literature in that direction, but the literature is too vast, I think, to really know everything about it. But again, I tend to focus more on the discrete case, although we started talking more about trying to do things in the continuous case.
Maybe I'll just say a few words if there are no more questions. I think that we should express our gratitude to Mikhail for this very nice course. He demonstrated the diversity of different topics in his lectures, and each lecture was about another topic, and all these topics were interesting. And are there any traits? Will be there? Do you leave us some PhD files?
I would be happy to, all of my lecture notes, I would be happy to give them to you if you want to post them online. I'd be more than happy to do that. Also, if anyone has any questions about any of the topics I've discussed, please feel free to email me about any questions. My email is, and hopefully you can read my handwriting, MGRABCHA at uncc.edu, and I'm very happy to answer any questions or get any comments, suggestions, or ideas, or anything else. So please feel free to email me. And yeah,
the video course will be available, and any questions maybe we can ask you.
Yes, sure. And yeah, I can, if you have someplace you can put the files, I'll be happy to make them available.
Okay, thank you very much.